morning, dear all. I'm Rajendra Nirtika from Department of Computer Science, Faculty of Science, University of Jaffna, Sri Lanka. My paper entitled on Loss Functions for Optimizing Kappa as the Evaluation Measure for Classifying Diabetic Retinopathy and Prostate Cancer Images. These are the outline of my presentation. First, the introduction to deep learning in medical imaging and the medical image classification task we have did. After that, the quadratic weighted Kappa as the evaluation measure and the loss function we have used for optimizing the Kappa. Finally, the experiments and results followed by discussion and conclusion with the references. Nowadays, medical imaging plays an important role in diagnosing the diseases, but there are some challenges. For example, lack of data, noisy images, human or technical errors. On the other hand, one of the deep learning techniques called convolutional neural network is a state-of-the-art method for medical imaging. It's going to learn multi-level features of a given input and classify them in a joint fashion. There are some evaluation measures used to evaluate the CNN model. For example, classification accuracy, quadratic weighted Kappa. But most of the medical image classification task uses the quadratic weighted Kappa as its evaluation measure because its classes are in an ordered fashion. We have used two medical image classification tasks. The first one is diabetic retinopathy image classification. Here, the labels are in an ordered fashion, like no diabetic retinopathy images, mild cases, moderate, and so on. The another one is prostate cancer images. Here, the images are labeled based on the grade of the cancer. And in the first image, this is an original image of the data set. Here you can see there are a lot of unwanted background information. So first we split this image and tile them as in the second image before our experiment. And here in both problems, the labels are in an ordered fashion. So we can say that these are the ordinal classification problem. And in the state-of-the-art methods, they have used quadratic weighted Kappa for the evaluation measure. So what is quadratic weighted Kappa? It's measure the level of agreement between the prediction of the system and the annotator. This is the equation to calculate the quadratic weighted Kappa score. Here, O is the observed agreement among the raters. It's identical to classification accuracy. E is the expected score. It's going to calculate by outer product between the actual histogram vector of outcomes and the predicted histogram vector. The weight W is the host associated with misclassifying instance. Here the weight going to consider the distance between the actual and the predicted labels. The loss functions are used to optimizing the evaluation measure. In some previous studies, they have used three types of loss function to optimize the quadratic weighted Kappa, such as cross entropy loss, ordinal regression-based loss, and the quadratic weighted Kappa loss. In our study, we are going to analyze the performance of these three loss functions in order to optimize the quadratic weighted Kappa. First, we will see the cross entropy loss. It's a widely used loss function and can be defined by this equation. Here, yi is the actual label of the ith image. And if we say there are 5 classes in the data set, then the network going to return 5 probability as the output for a single image. So PIL is the probability of the ith image belonging to a particular class. And the indicator function that returns 1 if the actual label is equal to the particular class, otherwise it's going to be 0. Here we can handle the class imbalance problems by just multiplying the class weights with the loss function. Here you can see this loss function not going to consider the distance between the predicted and the actual labels. So it's not a suitable loss function for ordinal classification problem. These two authors use cross-entropy loss in this domain. Ordinal regression-based loss is another loss function. It is a simple squared error formulation which measure the average of squared distance between the actual and the predicted label values. Here the yi is the actual label of the ith image and the hi is the predicted value of ith image. Because of this predicted value is unbounded, this loss function is highly sensitive to outliers. So, as another method, we have mapped these outputs to the number of classes using sigmoid function. Here also, you can see this loss function going to consider the difference between the actual and the predicted label. So, it's going to be a suitable loss function for the ordinal classification problem. In some previous work, ordinal regression have been used to optimize the quadratic weighted Kappa. The another one is quadratic weighted Kappa loss. We follow the steps provided in Beckham et al. To directly optimize the quadratic weighted Kappa as the loss function. As I said earlier, the quadratic weighted Kappa going to consider the distance between the actual and the predicted label. So, it also going to be a better loss function for ordinal classification problem. There are few attempts which directly optimize the quadratic weighted Kappa. In our experiment, we have used two different sizes of pre-trained ResNet architectures, and our input image size is, for both dataset, 512 squared pixels. And we use Adam optimizer with the initial learning rate 10 to the power minus 4. These are the results we have obtained for both datasets. Here you can see the quadratic weighted Kappa performs better than the other loss function in small network architecture. But if we consider the ordinal regression-based loss function, it performs better than the other loss function in large network architecture. From this result, we can say that cross-entropy loss is not an appropriate loss function for ordinal classification problem, as it does not consider the ordering of the classes. In our future work, we focus on investigating the reasons for the lower performance of quadratic weighted Kappa loss when large networks are used. These are the reference I have referred. Thank you.